Hello everyone, and thanks for watching Edupedia World videos. This is the second video for the topic longitudinal waves. In this video, we'll see some particular topics which you're already familiar with from the topic of transverse waves. We'll always assume that P is equal to P naught sine of omega t minus kx, and P naught will be B K S naught, and S will be the displacement, which will be 90 degrees ahead of the pressure. So whenever the pressure of a point is at its extremum, the displacement will be the equilibrium position, and whenever the displacement is at its extreme, the pressure will be at its equilibrium position. This P and P naught are not really the pressure, they are the excess pressure. They are the increase in pressure from its equilibrium value. Right. So now we'll study some topics which you've already seen in transverse waves. The first of them will be interference. Now what I've drawn here are tuning forks, and these are used to create sound waves of a particular frequency. You take a steel tuning fork and you hit it on a rubber pad and it will start vibrating, both the ends will start vibrating, and they can create sound waves of very particular specific frequencies. So in this case we've taken two tuning forks of the same frequency. They're in the same medium, so the wave velocity will be the same, and we want to study the interference of these two sound waves at a particular point. Let's say this distance is x and this distance is x plus delta x. So the net pressure here will be P1 plus P2, where P1 is the pressure due to the first tuning fork and P2 is the pressure due to the second tuning fork. That can be written if we assume both the pressures follow this equation: P01 sine omega t minus kx plus P02 sine omega t minus kx minus k delta x, right? Because it will be x plus delta x, right? So from this we know the actual answer. We've seen this before in vectors, in simple harmonic motion, and even in transverse waves. The net resultant will be P0 sine of omega t minus kx plus phi, where P0 will be root of P01 squared plus P02 squared plus 2 P01 P02 cos delta, and tan phi will be P02 sine delta by P01 plus P02 cos delta. I'm sure this is familiar to you by now. This is probably the fourth time we are seeing this equation. Whenever we have two vectors with different amplitudes and different phases, this is the net sum. In this case, delta will be equal to minus k delta x. Often we'll take it to be kx minus omega t, then it will be k delta x, but that is trivial. The ultimate result will be the same. Now we will have constructive interference. If delta is equal to 2n pi, that will mean P is equal to P01 plus P02, and we will have destructive. Again, we've seen this before for transverse waves. Now we are seeing this for sound waves. Delta will have to be 2n plus 1 pi. Right. In that case, P will be mod of P01 minus P02. I've only written mod because it's the absolute value. For example, if P01 is 2 and P02 is 5, the new pressure amplitude will be 3. Right? It will be displaced 180 degrees, but the amplitude always needs to be positive. Now delta is equal to 2n pi. What does that mean? That means k delta x or minus k delta x. That doesn't matter because n can go from n can take any integer value. K delta x is 2n pi, and k is 2 pi by lambda. So 2 pi cancel, and the result we get is delta x is equal to n lambda. Now k delta x is known as the phase difference. Delta x itself is known as the path difference. So if the path difference is an integral multiple of lambda, then we will have constructive interference. So we replace n by n plus half, we'll get the second equation. So for destructive interference, delta x is equal to n plus half lambda. If it's an integral multiple of lambda, constructive. If it's an integral multiple of lambda plus half lambda, then it will be destructive interference. And in that case, P will be mod of P01 minus P02. Now if the P0 square is equal to P01 square plus P02 square plus 2 P01 P02 cos delta, we could also write it in terms of the intensities of the waves. We saw in the first lecture that intensity is proportional to the square of the amplitude. So we can get the net intensity is equal to the first intensity plus the second intensity plus 2 root I1 root I2 cos delta. So this is an equation with which we can directly find out the resultant intensity if the individual intensities are given and the path difference or the phase difference is given. Now let's look at what happens when sound wave goes from one medium to another. I'll not give you the proof of this. We saw an example of this in transverse waves again. So right now you'll just accept it. The proof is not really in your course. And it is that whenever sound waves go from region 1 to region 2, if sound is going into the region where the wave velocity is smaller, let's say the wave velocity for 2 is smaller than velocity for 1, in that case the reflected wave is inverted. It suffers a phase change of pi. But if the speed in medium 2 is greater than the speed in medium 1, then the reflected wave is not inverted. This is exactly the same as in transverse waves, where we saw that when it goes from one rope to another rope, if it goes to a lighter rope, the reflected wave is not inverted, but if it goes in this way to the heavier rope, the reflected wave is inverted. Hey, this is not generally very useful to you, but a special case of this is very useful because now we will be looking at two types of organ pipes. Organ pipes is an instrument used to study interference of sound waves, and in that case we'll create standing waves. So there will be two types of organ pipes. One that will be open at both ends. We'll send sound from one side, it will go to the other side. This is air standard at normal pressure. It will get reflected, it will come back, it will get reflected and create standing waves. The other form will be an organ pipe which is closed at one end. So sound will enter from this place, it will change the pressure, it will reach this place, get reflected, get back to the starting point, get reflected again, and thus the motion will continue. And these are used to study interference in sound waves. Right. So let's look at what happens in these cases. In the first case, now an important thing to know here, to remember here rather, is that the pressure and the displacement are 90 degrees apart. So if the displacement is a node, the pressure will be an antinode, and if the pressure is a node, the displacement will be an antinode. Right. So both the descriptions are equivalent to understand from in this case. Let's look at the open organ pipe. Sound enters from this region, reaches this point. Now this point is a displacement antinode, and hence it's a pressure node. What does that mean? At this point there is no particular boundary restricting, unlike in this case, so the atoms are free to vibrate with as much amplitude as they want. So this will be a displacement antinode. If we wanted to look at it from the pressure point of view, this is air, right? You can have displacements in air in this place, but this outside air will always be at the P atmospheric pressure. So this particular end of the organ pipe will never have its pressure change. Even if its pressure changes by a slight amount, let's say it increases by a slight amount, those molecules will immediately go outside and the pressure will stay the same. So the pressure at this end can never change. So it is the pressure node and the displacement antinode, right? That is what open ends are. So what happens with open ends? Since it is a pressure node, sound wave when it is reflected by the open end has a phase change of pi. Just like when we had ropes in which we had, let's say, waves, and when they were fixed at one end, if they were fixed at one end, then the reflected wave had a phase change of pi, right? So we can imagine this just like this, because pressure is more important than displacement. So at this end it is a pressure node. Pressure cannot change at all. this end was the displacement node for transverse waves. So when you have a node, the reflected wave is inverted. As opposed to that, when you had the free end completely free, then this was the pressure antinode, which it is in this case. So this point, the pressure can change by a huge amount. There is nothing to restrict it on the other side. Also, this is the fixed end because this is fixed to this particular closed wall. So this end is a displacement node. These points are not moving anywhere. They can't move anywhere. And hence it's a pressure antinode. And that would be like a rope in which one end is completely free to move up or down wherever it wants. So in that case, the reflected wave will have no phase change. Right. So whenever sound is reflected from an open end, it is a pressure node because pressure cannot change at all. Right. If pressure has to be the pressure equilibrium at this point, then the excess pressure has to be 0 at this point. Just like the displacement had to be 0 at this point. If displacement is 0 at this point or pressure is 0 at this point, just for the sake of clarity, displacement I'm only showing just so you know, but the important thing is pressure in sound waves. We talked about that earlier. So if this is a displacement node, this point is not allowed to move anywhere. That is only possible if the reflected wave is inverted, so that when they add up, they get 0 at this point. Similarly, if this is a pressure node, it is only possible if the reflected wave is inverted. This is the pressure antinode. Pressure changes by a huge amount here. So there will be no phase change in this case. Now let's look at these two in a little bit more detail. First, let's look at an organ pipe that is open at both ends. So sound waves are sent from one side, they'll go to the other side, they'll come back. The total phase change between a wave entering here now and a wave going, getting reflected, coming back, getting reflected again and going, because these two are the ways which will get interfered, right? So the phase difference total between them will be, first of all, 2 times the length, right? So it will be 2 pi by lambda k times twice the length plus a phase change of pi will occur from this end, plus a phase change of pi will occur from this end as well. So this is the total phase difference between the wave that was sent initially and the wave which goes through the length, is reflected once, comes back, is reflected again. Right. So this 2 pi we can always just end up neglecting because the difference of 2 pi is no difference at all. So what we get is delta is equal to 2 pi by lambda times 2L. Right. What should this be equal to? If this is equal to 2n pi, then we know that there will be constructive interference, and hence constructive interference will lead to standing waves, just like in transverse waves. Right. So what this gives me is 2 pi and 2 pi will cancel. What this gives me is L is equal to n lambda by 2. So for standing waves to be set up in an open organ pipe, the length of the organ pipe must be an integral multiple of lambda by 2. Right. And in that case, the frequency will be nv by 2L, because we know that lambda mu is the wave velocity. Right. So these are the two equations for standing waves for an open organ pipe. Let's look at how these waves will look. Right. So I'll just draw the diagrams now. We have L is equal to n lambda by 2, and we have mu is equal to nv by 2L. Now all the terminology, n is greater than equal to 1. All the terminology I told you last time is valid here as well. The harmonics and the overtones. So the third harmonic will be 3v by 2L, and the third overtone will be 4v by 2L. If you don't remember that, it was quite important. I suggest you go back to the video on transverse waves and look at that again. What harmonics are and what overtones are. They tend to confuse students sometimes. Right? So let's draw some open organ pipes. I'll first draw the pressure variation, then just for the sake of clarity, I'll draw the displacement variations as well. Though you always need to remember that pressure variations are important because sound waves are created, received by pressure variations. The eardrum senses pressure variations, not displacement variations. Right. So let's take the first case, n is equal to 1. In that case, L is equal to lambda by 2. Right. So in that case, we'll draw pressure and displacement. So in that case, this is a sort of pressure wave that is formed. The ends, we know that twice this is one wavelength, right? The ends are pressure nodes. The pressure at the ends will always stay the atmospheric pressure because they are completely connected to the atmosphere outside. So the ends are the nodes. The midpoint is the antinode. You have one antinode between two nodes. When n is equal to 2, you have L is equal to lambda. In that case, this is, I apologize for the not really symmetric drawing, but I'm sure you can understand how it must be. So in that case, this is the wave that is formed. The ends will always be pressure nodes. Just remember that. If it is an open end, the end will be a pressure node because the pressure has to be atmospheric pressure. There will be one node in the middle. And obviously for this, it will be something like this. For these pressure waves, I can draw the displacement waves as well. If this is the pressure node, then this has to be the displacement antinode, right? And if this is the pressure antinode, it has to be the displacement node. So the displacement will actually be like this. It will be maximum at the endpoints because here the atoms are free to move. There is nothing restricting them, atoms or molecules. And in the middle, there will be a node, right? Then you can draw this for the other two. I'm not going to draw them. I'm not going to waste time. Let's look at the closed organ pipe now. Right. So this is the closed organ pipe. Let's say length is L. Sound waves go in, then they are reflected, come back reflected. So the total phase difference between these, first of all, it will be 2 pi by lambda times 2L. Then plus. Now, when it is reflected from this closed end is a pressure antinode, so the wave will not be inverted. So there will be no phase difference when it is reflected from this closed end. When it comes back and is reflected from this open end, it will suffer a phase difference of pi. Right? So this is the net phase difference, and this needs to be equal to 2n pi for constructive interference to take place. So from that we can get the equation. Let's say this is 2 pi times half. So 2 pi and 2 pi will cancel. We'll get 2L by lambda plus half is equal to n. Right. From that we can get L is equal to n minus half times lambda by 2. So in the previous case it was L is equal to n lambda by 2. Now it's n minus half lambda by 2. From this equation you can get frequency, that is equal to n minus half V by 2L, right, and n is greater than equal to 1. So let's draw the figures in this case. If n is equal to 1, then L is equal to lambda by 4. So in that case, for pressure, it is like this. Let me just draw the figure more clearly here. Yeah, so this is the pressure. This is a fourth of a wavelength. If this goes to the other end, it would be a half of a wavelength and then a complete wavelength. So this is 1/4 of a wavelength. We know that the ends have to be pressure antinodes. And we know that these points have to be pressure nodes. Alternatively, the displacement in this case would be like this. These ends have to be displacement nodes. They can't move, right? Because they're stuck to this wall. And this will be the displacement antinode. I'll just draw one more for the pressure one. N is equal to 1. Sorry, n is equal to 2. For n is equal to 2, L is equal to n minus half lambda by 2. That is 2 minus half is 3 by 4. 3 by 2 and so this 3 by 4. This is 3 lambda by 4. So again, we know the things that are true. We know that this is a node and this is an antinode. So in that case, it is like this. Yeah, sorry, I didn't make it like this. This is half a wavelength and this is a quarter of a wavelength. So you have one antinode and one node in between the two ends. These are, I'll tell you the type of questions that can be made on this. They can tell you that the string is vibrating, not the string is vibrating, that's transverse waves. They can tell you that the closed organ pipe is resonating in the third harmonic mode, right? And then they'll ask you what is the length of the tube that is required. Or they can just ask you that if it is vibrating in the fifth overtone, how many antinodes are there between the two ends. Right. So this completes interference. Let's move on to another small topic but quite interesting, and that is the phenomena of beats. Up till now we've seen interference of two sound waves which have the exact same frequency, and that is necessary because if they don't have the same frequency, then there will not be any periodic motion, nothing will repeat itself, and it will not even be a wave. However, a particular interesting thing happens when two waves have their frequencies near each other but not exactly the same, right? So in that case, when we write P is equal to P1 plus P2, we can write it as P01 sine of omega 1 times T minus x by V plus P02 sine of omega 2 times T minus x by V. Right. So you can do sin C plus sin D here, and you can use the formulas trigonometry wise, and the answer you'll get is this is equal to 2 P0 cos of delta omega by 2 T minus x by V sine of omega times T minus x by V, where omega is omega 1 plus omega 2 by 2 and delta omega is mod of omega 1 minus omega 2. Right. So you can just substitute this and see that this will be valid. The important thing is this: the interference of these two vibrates like a simple harmonic motion with an amplitude 2 P0 cos of delta omega by 2 T minus x by V. Now we've assumed that these are close together, so delta omega is quite small. So this particular thing repeats itself after a long time. Initially it is 2 P0 if this whole thing is 0, and then it goes to 0, minus 2 P0 0, but this changes much more slowly compared to this. This changes very fast. So that creates a very interesting result. I'll try to explain that graphically. So let's say the first one goes like this. It goes very fast. And the second one, this one, the delta omega by 2 term moves very slowly, and it goes like this. Right. So when you multiply these two, these points will be multiplied by 0. These points will be multiplied by 0. These points will be multiplied by 0. These points will be multiplied by highly positive numbers. These points will be multiplied by high numbers as well. So the net product of these comes out to be something like this. So you have the standard sine wave, except it's multiplied by a bigger wave. So there are points when the amplitude is small, there are points when the amplitude is large. Right. So these are the sort of waves that are created, and these lead to a periodic increase and decrease of amplitude, which is also a periodic increase and decrease in intensity. Right. And the amplitude varies with frequency delta mu by 2, because in the amplitude we had delta omega by 2. Delta omega by 2 was the angular frequency, delta mu by 2 is the frequency of the variation of the amplitude. Now the intensity is proportional to the amplitude squared, right? This should be written as P if you're talking about pressure amplitude. So the intensity is always positive, right? The amplitude can be positive, negative, the intensity is always positive. So it varies at twice the speed, right? This is analogous to the kinetic energy varies as twice the frequency of the velocity in simple harmonic motion, right? Because it's v squared, it's always positive. So what that tells us is the intensity varies with frequency delta mu. And this is the most important result of beats. So if you have interference of two sound waves, one of them is a frequency of 100 Hertz, the other has a frequency of 102 Hertz, then what you will hear is interference in which the sound will periodically increase and decrease in volume, and the frequency of that periodic variation will be 2 Hertz, 2 times a second. And this, some of you might be familiar with this. This is what musicians are listening to when they tune their guitars, right? So if you want to tune your guitar, these are the strings of a guitar, you know that this has to vibrate with a harmonic of the frequency which it vibrates when you put your finger here. So this is the length which is allowed to vibrate. So these two are supposed to have the same frequency. So what they'll do is they'll plug both of them together, and they'll listen to something like this, where the intensity will keep on increasing and decreasing. And at that period, as it keeps on increasing, the difference keeps on decreasing until eventually you don't hear any beats. So if you plug two strings which are near the same frequency, you'll hear a sound like this, in which the sound intensity keeps increasing and decreasing and increasing and decreasing. That should be familiar to some of you. The final topic left for sound waves is a very important topic called Doppler effect. Now here I'm going to do something which is slightly untraditional. Even though the derivation of the formula for Doppler effect is in your course, I'm not going to show it here. I will motivate it here by explaining it a little bit, but the derivation for Doppler effect requires you to really read about it and think for it some time, because the plus and minus signs need to be clear, because they are very important, right? So I just suggest that you look at the derivation of Doppler effect from a textbook and try to understand it properly. I will try to motivate it here as well and try to explain as much as I can. But it's not really very easy to explain in 5 to 6 minutes. You need to really think about it for an hour or so before you really get it. Though it's not hard. I have to say, it's not hard at all. Right. So what the Doppler effect is it tells us that the frequency of a sound changes as the speed of the medium changes. The speed of the medium, or the speed of the source, or the speed of the observer changes. So you've all probably experienced this if you've stood next to a train. As the train is approaching you, the frequency seems to be high, the frequency of the sound of the train, or if it whistles, but the moment it passes you, the frequency seems to drop by a significant amount. It's not a continuous process. It does not go from a high value to a low value through a period of time. The moment the train crosses you, instantaneously the frequency drops by a certain amount, right? So why does that happen? Let's take this to be the source of sound and this to be the observer. What Doppler effect is basically is, I'll just write the definition here first. It is the apparent change in frequency due to the motion of the source, just spelling mistakes, or the observer. So the frequency of the sound waves does not change, but the apparent frequency changes. That can happen either when the source is moving, or when the observer is moving, or both of them are moving. So let's see what happens if the source is moving. The source is emitting some sound waves with a particular frequency and amplitude at speed, and let's say the source is moving towards the right with a certain speed. So let's take t is equal to 0 at a time when the source emits a certain wave. That wave takes a particular time, let's say t is equal to 5 seconds to reach this point, right? So this observer listens to the first sound at t is equal to 5. The first, this wave, let's assume this is the first wave at t is equal to 5, right? Now let's assume the second wave is emitted at t is equal to 1 seconds, right? Ordinarily, what would happen if the source was not moving? It would be emitted at t is equal to 1 second, it would be heard at t is equal to 6 seconds, then this would be emitted at t is equal to 2 seconds, t is equal to 3 seconds, and they would be heard at t is equal to 7 and t is equal to 8 seconds. So one particular wave is emitted every second, and one particular wave is heard every second, right? And the frequency is nothing but the number of crests or troughs in a unit time. So the frequency emitted and the frequency observed are the same if the source was not moving. But let's say the source is moving. Then when the first wave was emitted, the source was here and this was a certain amount of distance. When the second wave is emitted, the source has moved nearby and this distance has decreased. So the second wave will take a time smaller than 5 seconds to reach this. Let's say it takes a time of 4.8 seconds instead of 5 seconds. Right? So the second wave emitted at t is equal to 1 will not be heard at t is equal to 6. It will be heard at t is equal to 5.8. Right? When the third wave is emitted at t is equal to 2, this will have moved a certain more amount such that now the time taken to travel will be 4.6 seconds. So the third sound wave will be heard at 2 plus 4.6, that is 6.6 seconds. And similarly the third would be at 7.4 seconds. Right? So we see that though one wave is emitted per second, we hear one wave every 0.8 seconds. Or another way to say it would be we hear 1.25 waves every second. Right? Now in the actual derivation you take the speed of this to be v1, to be v2, to be lambda, and you just derive it mathematically. I am doing basically that except for slightly easy values such as 1 second and 5 seconds to make it clearer. Right? So the wave emitted at t is equal to 0 is heard at t is equal to 5. The wave emitted at t is equal to 1 is not heard at t is equal to 6. It's heard slightly before that because the source has already moved some distance. It's heard at 5.8. The wave emitted at t is equal to 2 seconds when the source is here is heard at t is equal to 6 seconds. So instead of hearing one wave every second, we are hearing one wave every 0.8 seconds or 1.25 waves every second. So the frequency which the observer hears, mu observed, is greater than the mu of the source. And we know obviously from intuition that the greater the speed of the source, the greater the change will be and the greater the mu observed will be. Right? So this is why when a source starts moving, the frequency heard by the observer changes. When the source is moving towards you, the frequency increases. Now let's say this source is the train and you are standing here, and now the train is gone past you. So now every wave it emits will take a longer and longer time to reach. So let's say it emits a wave at t is equal to 10 seconds which reaches you at t is equal to 11. The next wave emitted at t is equal to 11 will not reach you at t is equal to 12. It will reach you at t is equal to 12.1. So now you will hear smaller and smaller number of waves every second because each wave takes a longer time to travel. So the frequency will decrease. Similarly, now you can think about it for yourself. If the source is stationary but the observer is moving, then also the frequency heard by the observer will change because each wave will travel a different amount of time. Right? This is the ultimate concept from which the Doppler effect is derived. Now I'm going to just write the standard formula for the frequency, and you can look up the actual derivation anywhere, or I would suggest if you understood this, you try to derive the formulas yourself first. That will teach you a lot, even if you don't get it. Right? So the Doppler effect says that mu apparent is equal to V plus minus U naught by V plus minus US times mu naught. Mu apparent is obvious, it is the apparent frequency. Mu naught is the original frequency. V is the speed, this is V, of sound. U naught is the speed of the observer, may or may not be 0. US is the speed of the source, may or may not be 0. If both U naught and US are 0, then these two are 0, V and V cancel, and V apparent is mu naught. But if one of the two is changing, then mu apparent is different from mu naught. Now what is this plus and minus about? Again, that is one of the reasons I chose not to do the complete derivation for you, because the signs tend to become confusing. So I'll tell you a simple rule which tells you whether plus or minus should be applied. A decrease in distance means an increase in frequency. Right? So let's say this is the source and this is the observer. If the observer is stationary and the source is moving, if the source moves towards the right, then the distance between them is decreasing. That means the frequency should increase. Now you just go back to the equation. If the frequency is increasing and we need US, then there should be a minus sign, right? Because this should be greater than 1. But if the source is moving towards the left, then the distance between them is increasing. That means the frequency is decreasing. So you'll have to use a plus here. Easy enough, right? If the source isn't moving but the observer is moving, then if it's moving towards the left, then you put a plus or a minus depending on such that the frequency should increase. So a plus. But if the source is moving, the observer is moving towards the right, we put a minus. If both of them are moving, let's say this is moving towards the right and this is also moving towards the right, then the source is moving to decrease the distance. So the source will increase the frequency, so you'll have a minus. The observer is moving to increase the distance, right? So the observer will decrease the frequency, so it will also be a minus, right? So it will just be V U naught. The only thing I truly need to remember in this, personally for me, is that observer comes first and source comes second. All I need to know is the observer comes in the numerator and the source comes in the denominator, and the decrease in distance corresponds to increase in frequency, and after that I'm able to solve any Doppler effect question. Right, so if you just standard questions will be asked, there is a source which has a frequency of 100 Hertz and there is an observer which is moving towards it with the speed of 20 meters per second. The speed of sound is 330 meters per second. What is the apparent frequency heard by this observer? So the distance is decreasing, that means frequency is increasing. So US we know is 0 in this case, frequency is increasing, so this should be a plus. So this will be the final answer. That is 350 divided by 330 into mu naught. So 35 by 33 mu naught. So 35 by 33 times 100. Right? Easy enough. One small final thing. Sometimes the source and the observer will not be moving along the same direction. Let's say this is the line joining them. The source is moving in this direction and the observer is moving in this direction. Theta 1, theta 2. So that's easy enough. In the formula where you have plus minus u naught and plus minus us, u naught and us should be the speeds of the source and observer along the line joining them. So if this is moving at an angle theta 2 to the line joining them, then u naught, and if this is us, then this will simply be us cos theta 2, and this will be u naught cos theta 1. So the components should be taken along the line joining them. There are 2-3 other small things which I'll just mention because they're not really mentioned any particular place in a book, but you should know them. One is obviously the speed of sound. So I'll just write V so it's not confused with U source. That is 332 meter per second in air. Another thing, for a human ear to hear a sound, the frequency must be greater than 20 Hertz. Anything smaller than 20 Hertz is called infrasonic, and the frequency must be less than 20,000 Hertz. A frequency greater than 20,000 Hertz is called ultrasonic. Right. Another thing, for a human ear to be able to distinguish between beats, they must happen with a frequency less than 16 Hertz. If the frequency changes more than 16 times a second, the human ear will not be able to hear beats. Right. And finally, another small concept, the speed of an object divided by the speed of sound is called the Mach number. So if in the question it's mentioned that a jet is traveling at 0.5 Mach number, that means the speed of the jet is 0.5 times 332 meters per second, or it's 0.5 times the speed of sound. This completes sound waves and longitudinal waves in general. Thank you.